Stochastic process. In probability theory and related fields, a stochastic or random process is a mathematical object usually defined as a family of random variables. Stochastic processes are widely used as mathematical models of systems and phenomena that appear to vary in a random manner. Examples include the growth of a bacterial population, an electrical current fluctuating due to thermal noise, or the movement of a gas molecule. Stochastic processes have applications in many disciplines such as biology, chemistry, ecology, neuroscience, physics, image processing, signal processing, control theory, information theory, computer science, cryptography, and telecommunications. Furthermore, seemingly random changes in financial markets have motivated the extensive use of stochastic processes in finance. Applications and the study of phenomena have in turn inspired the proposal of new stochastic processes. Examples of such stochastic processes include the Wiener process, or Brownian motion process, used by Louis Bachelier to study price changes on the Paris Bourse, and the Poisson process, used by A.K. Erlang to study the number of phone calls occurring in a certain period of time. These two stochastic processes are considered the most important and central in the theory of stochastic processes, and were discovered repeatedly and independently, both before and after Bachelier and Erlang, in different settings and countries. The term random function is also used to refer to a stochastic or random process, because a stochastic process can also be interpreted as a random element in a function space. The terms stochastic process and random process are used interchangeably, often with no specific mathematical space for the set that indexes the random variables. But often these two terms are used when the random variables are indexed by the integers or an interval of the real line. If the random variables are indexed by the Cartesian plane or some higher dimensional Euclidean space, then the collection of random variables is usually called a random field instead. The values of a stochastic process are not always numbers and can be vectors or other mathematical objects. Based on their mathematical properties, stochastic processes can be grouped into various categories, which include random walks, martingales, Markov processes, Lévy processes, Gaussian processes, random fields, renewal processes, and branching processes. The study of stochastic processes uses mathematical knowledge and techniques from probability, calculus, linear algebra, set theory, and topology, as well as branches of mathematical analysis such as real analysis, measure theory, Fourier analysis, and functional analysis. The theory of stochastic processes is considered to be an important contribution to mathematics, and it continues to be an active topic of research for both theoretical reasons and applications. Introduction. A stochastic or random process can be defined as a collection of random variables that is indexed by some mathematical set, meaning that each random variable of the stochastic process is uniquely associated with an element in the set. The set used to index the random variables is called the index set. Historically, the index set was some subset of the real line, such as the natural numbers, giving the index set the interpretation of time. Each random variable in the collection takes values from the same mathematical space known as the state space. This state space can be, for example, the integers, the real line or n, \n, dimensional Euclidean space. An increment is the amount that a stochastic process changes between two index values, often interpreted as 2 points in time. A stochastic process can have many outcomes due to its randomness, and a single outcome of a stochastic process is called, among other names, a sample function or realization. Classifications. A stochastic process can be classified in different ways, for example, by its state space, its index set, or the dependence among the random variables. One common way of classification is by the cardinality of the index set and the state space. When interpreted as time, if the index set of a stochastic process has a finite or countable number of elements, such as a finite set of numbers, the set of integers, or the natural numbers, then the stochastic process is said to be in discrete time. If the index set is some interval of the real line, then time is said to be continuous. The two types of stochastic processes are respectively referred to as discrete time and continuous time stochastic processes. Discrete time stochastic processes are considered easier to study because continuous time processes require more advanced mathematical techniques and knowledge, particularly due to the index set being uncountable. If the index set is the integers or some subset of them, then the stochastic process can also be called a random sequence. If the state space is the integers or natural numbers, then the stochastic process is called a discrete or integer-valued stochastic process. If the state space is the real line, then the stochastic process is referred to as a real-valued stochastic process or a process with continuous state space. If the state space is n \n dimensional Euclidean space, then the stochastic process is called a 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 n \n dimensional vector process or n \n vector process. Etymology. The word stochastic in English was originally used as an adjective with the definition pertaining to conjecturing and stemming from a Greek word meaning to aim at a mark, guess, and the Oxford English Dictionary gives the year 1662 as its earliest occurrence. In his work on probability Ars Conjectandi, originally published in Latin in 1713, Jacob Bernoulli used the phrase ars conjectandi sive stochastis, which has been translated to the art of conjecturing or stochastics. This phrase was used with reference to Bernoulli by Ladislaus Bortkiewicz, who in 1917 wrote in German the word stochastic with a sense meaning random. The term stochastic process first appeared in English in a 1934 paper by Joseph Dube. For the term and a specific mathematical definition, Dube cited another 1934 paper where the term stochastischer process was used in German by Alexander Kinchen, though the German term had been used earlier, for example, by Andrei Kolmogorov in 1931. According to the Oxford English Dictionary, early occurrences of the word random in English with its current meaning, which relates to chance or luck, date back to the 16th century, while earlier recorded usages started in the 14th century as a noun meaning impetuosity, great speed, force, or violence in riding, running, striking, etc. The word itself comes from a Middle French word meaning speed, haste, and it is probably derived from a French verb meaning to run or to gallop. The first written appearance of the term random process predates stochastic process, which the Oxford English Dictionary also gives as a synonym, and was used in an article by Francis Edgeworth published in 1888. Terminology. The definition of a stochastic process varies, but a stochastic process is traditionally defined as a collection of random variables indexed by some set. The terms random process and stochastic process are considered synonyms and are used interchangeably, without the index set being precisely specified. Both collection or family are used while instead of index set. Sometimes the terms parameter set or parameter space are used. The term random function is also used to refer to a stochastic or random process, though sometimes it is only used when the stochastic process takes real values. This term is also used when the index sets are mathematical spaces other than the real line, while the terms stochastic process and random process are usually used when the index set is interpreted as time, and other terms are used such as random field when the index set is n \n dimensional Euclidean space r n \math Rn, or manifold. Notation. Examples: Bernoulli process, random walk, Wiener process, Poisson process. The Poisson process is a stochastic process that has different forms and definitions. It can be defined as a counting process, which is a stochastic process that represents the random number of points or events up to some time. The number of points of the process that are located in the interval from 0 to some given time is a Poisson random variable that depends on that time and some parameter. This process has the natural numbers as its state space and the non-negative numbers as its index set. This process is also called the Poisson counting process, since it can be interpreted as an example of a counting process. If a Poisson process is defined with a single positive constant, then the process is called a homogeneous Poisson process. The homogeneous Poisson process is a member of important classes of stochastic processes, such as Markov processes and Lévy processes. The homogeneous Poisson process can be defined and generalized in different ways. It can be defined such that its index set is the real line, and this stochastic process is also called the stationary Poisson process. If the parameter constant of the Poisson process is replaced with some non-negative integrable function of t, \displaystyle t, the resulting process is called an inhomogeneous or non-homogeneous Poisson process, where the average density of points of the process is no longer constant. Serving as a fundamental process in queuing theory, the Poisson process is an important process for mathematical models, where it finds applications for models of events randomly occurring in certain time windows. Defined on the real line, the Poisson process can be interpreted as a stochastic process among other random objects. But then it can be defined on the n \displaystyle n dimensional Euclidean space or other mathematical spaces, where it is often interpreted as a random set or a random counting measure instead of a stochastic process. In this setting, the Poisson process, also called the Poisson point process, is one of the most important objects in probability theory, both for applications and theoretical reasons. But it has been remarked that the Poisson process does not receive as much attention as it should, partly due to it often being considered just on the real line and not on other mathematical spaces. Definitions: stochastic process, indexed set, dex set, state space, the mathematical space S \displaystyle S of a stochastic process is called its state space. This mathematical space can be defined using integers, real lines, n \displaystyle n, dimensional Euclidean spaces, complex planes, or more abstract mathematical spaces. The state space is defined using elements that reflect the different values that the stochastic process can take. Sample function, increment, further definitions, law, finite dimensional probability distributions, stationarity, filtration, modification, indistinguishable, separability, independence, uncorrelatedness. Independence implies uncorrelatedness. If two stochastic processes x \displaystyle x tile x and y \displaystyle y are independent, then they are also uncorrelated. Orthogonality, Skorokhod space, regularity, hilarity. In the context of mathematical construction of stochastic processes, the term regularity is used when discussing and assuming certain conditions for a stochastic process to resolve possible construction issues. For example, to study stochastic processes with uncountable index sets, it is assumed that the stochastic process adheres. Further examples: Markov processes and chains. Markov processes are stochastic processes, traditionally in discrete or continuous time, that have the Markov property, which means the next value of the Markov process depends on the current value, but it is conditionally independent of the previous values of the stochastic process. In other words, the behavior of the process in the future is stochastically independent of its behavior in the past, given the current state of the process. The Brownian motion process and the Poisson process in one dimension are both examples of Markov processes in continuous time, while random walks on the integers and the gambler's ruin problem are examples of Markov processes in discrete time. A Markov chain is a type of Markov process that has either discrete state space or discrete index set, often representing time, but the precise definition of a Markov chain varies. For example, it is common to define a Markov chain as a Markov process in either discrete or continuous time with a countable state space, thus regardless of the nature of time, but it has been also common to define a Markov chain as having discrete time in either countable or continuous state space, thus regardless of the state space. It has been argued that the first definition of a Markov chain, where it has discrete time, now tends to be used, despite the second definition having been used by researchers like Joseph Dube and Kai-Lai Chung. Markov processes form an important class of stochastic processes and have applications in many areas. For example, they are the basis for a general stochastic simulation method known as Markov chain Monte Carlo, which is used for simulating random objects with specific probability distributions, and has found application in Bayesian statistics. The concept of the Markov property was originally for stochastic processes in continuous and discrete time, but the property has been adapted for other index sets such as n backslash display style n dimensional Euclidean space, which results in collections of random variables known as Markov random fields. Martingale, Lévy process. Random field. A random field is a collection of random variables indexed by n backslash display style n dimensional Euclidean space or some manifold. In general, a random field can be considered an example of a stochastic or random process where the index set is not necessarily a subset of the real line. But there is a convention that an indexed collection of random variables is called a random field when the index has two or more dimensions. If the specific definition of a stochastic process requires the index set to be a subset of the real line, then the random field can be considered as a generalization of stochastic process. Point process. A point process is a collection of points randomly located on some mathematical space such as the real line n backslash display style n dimensional Euclidean space or more abstract spaces. Sometimes the term point process is not preferred, as historically the word process denoted an evolution of some system in time, so a point process is also called a random point field. There are different interpretations of a point process, such a random counting measure or a random set. Some authors regard a point process and stochastic process as two different objects, such that a point process is a random object that arises from or is associated with a stochastic process, though it has been remarked that the difference between point processes and stochastic processes is not clear. Other authors consider a point process as a stochastic process, where the process is indexed by sets of the underlying space on which it is defined, such as the real line or n backslash display style n dimensional Euclidean space. Other stochastic processes, such as renewal and counting processes, are studied in the theory of point processes. History. Early probability theory. Probability theory has its origins in games of chance, which have a long history, with some games being played thousands of years ago, but very little analysis on them was done in terms of probability. The year 1654 is often considered the birth of probability theory, when French mathematicians Pierre Fermat and Blaise Pascal had a written correspondence on probability, motivated by a gambling problem. But there was earlier mathematical work done on the probability of gambling games such as Liber de Ludo Ali by Girolamo Cardano, written in the 16th century but posthumously published later in 1663. After Cardano, Jacob Bernoulli wrote Ars Conjectandi, which is considered a significant event in the history of probability theory. Bernoulli's book was published, also posthumously, in 1713 and inspired many mathematicians to study probability. But despite some renowned mathematicians contributing to probability theory, such as Pierre-Simon Laplace, Abraham de Moivre, Carl Gauss, Simon Poisson, and Pafnuty Chebyshev, most of the mathematical community did not consider probability theory to be part of mathematics until the 20th century. Statistical mechanics. In the physical sciences, scientists developed in the 19th century the discipline of statistical mechanics, where physical systems, such as containers filled with gases, can be regarded or treated mathematically as collections of many moving particles. Although there were attempts to incorporate randomness into statistical physics by some scientists, such as Rudolf Clausius, most of the work had little or no randomness. This changed in 1859, when James Clerk Maxwell contributed significantly to the field, more specifically to the kinetic theory of gases, by presenting work where he assumed the gas particles move in random directions at random velocities. The kinetic theory of gases and statistical physics continued to be developed in the second half of the 19th century, with work done chiefly by Clausius, Ludwig Boltzmann, and Josiah Gibbs, which would later have an influence on Albert Einstein's mathematical model for Brownian movement. Measure theory and probability theory. At the International Congress of Mathematicians in Paris in 1900, David Hilbert presented a list of mathematical problems, where his sixth problem asked for a mathematical treatment of physics and probability involving axioms. Around the start of the 20th century, mathematicians developed measure theory, a branch of mathematics for studying integrals of mathematical functions, where two of the founders were French mathematicians, Henri Lebesgue and Émile Borel. In 1925, another French mathematician, Paul Lévy, published the first probability book that used ideas from measure theory. In 1920s, fundamental contributions to probability theory were made in the Soviet Union by mathematicians such as Sergei Bernstein, Alexander Khinchin, and Andrei Kolmogorov. Kolmogorov published in 1929 his first attempt at presenting a mathematical foundation based on measure theory for probability theory. In the early 1930s, Khinchin and Kolmogorov set up probability seminars, which were attended by researchers such as Eugene Slutsky and Nikolai Smirnov, and Khinchin gave the first mathematical definition of a stochastic process as a set of random variables indexed by the real line. Birth of modern probability theory. In 1933, Andrei Kolmogorov published in German his book on the foundations of probability theory titled Grundbegriff der Wahrscheinlichkeitsrechnung, where Kolmogorov used measure theory to develop an axiomatic framework for probability theory. The publication of this book is now widely considered to be the birth of modern probability theory, when the theories of probability and stochastic processes became parts of mathematics. Arts of Mathematics. After the publication of Kolmogorov's book, further fundamental work on probability theory and stochastic processes was done by Khinchin and Kolmogorov, as well as other mathematicians such as Joseph Dube, William Feller, Maurice Fréchet, Paul Lévy, Wolfgang Doblin, and Harold Kramer. Decades later, Kramer referred to the 1930s as the heroic period of mathematical probability theory. World War II greatly interrupted the development of probability theory, causing, for example, the migration of Feller from Sweden to the United States of America and the death of Doblin, considered now a pioneer in stochastic processes. Stochastic processes after World War II. After World War II, the study of probability theory and stochastic processes gained more attention from mathematicians, with significant contributions made in many areas of probability and mathematics, as well as the creation of new areas. Starting in the 1940s, Kiyoshi Ito published papers developing the field of stochastic calculus, which involves stochastic integrals and stochastic differential equations based on the Wiener or Brownian motion process. Also starting in the 1940s, connections were made between stochastic processes, particularly martingales, and the mathematical field of potential theory, with early ideas by Shizuo Kakutani and then later work by Joseph Dube. Further work, considered pioneering, was done by Gilbert Hunt in the 1950s, connecting Markov processes and potential theory, which had a significant effect on the theory of Lévy processes and led to more interest in studying Markov processes with methods developed by Ito. In 1953, Dube published his book Stochastic Processes, which had a strong influence on the theory of stochastic processes and stressed the importance of measure theory and probability. Dube also chiefly developed the theory of martingales, with later substantial contributions by Paul-André Mayer. Earlier work had been carried out by Sergei Bernstein, Paul Lévy, and Jean Ville, the latter adopting the term martingale for the stochastic process. Methods from the theory of martingales became popular for solving various probability problems. Techniques and theory were developed to study Markov processes and then applied to martingales. Conversely, methods from the theory of martingales were established to treat Markov processes. Other fields of probability were developed and used to study stochastic processes, with one main approach being the theory of large deviations. The theory has many applications in statistical physics, among other fields, and has core ideas going back to at least the 1930s. Later in the 1960s and 1970s, fundamental work was done by Alexander Wenzel in the Soviet Union and Monroe D. Donsker and Srinivasa Varadhan in the United States of America, which would later result in Varadhan winning the 2007 Abel Prize. In the 1990s and 2000s, the theories of Schramm-Lohner evolution and rough paths were introduced and developed to study stochastic processes and other mathematical objects in probability theory, which respectively resulted in Fields medals being awarded to Wendelin Werner in 2008 and to Martin Harrer in 2014. The theory of stochastic processes still continues to be a focus of research, with yearly international conferences on the topic of stochastic processes. Discoveries of specific stochastic processes. Although Khinchin gave mathematical definitions of stochastic processes in the 1930s, specific stochastic processes had already been discovered in different settings, such as the Brownian motion process and the Poisson process. Some families of stochastic processes, such as point processes or renewal processes, have long and complex histories, stretching back centuries. Bernoulli process. The Bernoulli process, which can serve as a mathematical model for flipping a biased coin, is possibly the first stochastic process to have been studied. The process is a sequence of independent Bernoulli trials, which are named after Jacob Bernoulli, who used them to study games of chance, including probability problems proposed and studied earlier by Christian Huygens. Bernoulli's work, including the Bernoulli process, were published in his book Ars Conjectandi in 1713. Random walks. In 1905, Carl Pearson coined the term random walk while posing a problem describing a random walk on the plane, which was motivated by an application in biology. But such problems involving random walks had already been studied in other fields. Certain gambling problems that were studied centuries earlier can be considered as problems involving random walks. For example, the problem known as the gambler's ruin is based on a simple random walk and is an example of a random walk with absorbing barriers. Pascal, Fermat, and Hyans all gave numerical solutions to this problem without detailing their methods, and then more detailed solutions were presented by Jacob Bernoulli and Abraham de Moivre. For random walks in n \n dimensional integer lattices, George Polya published in 1919 and 1921 work where he studied the probability of a symmetric random walk returning to a previous position in the lattice. Polya showed that a symmetric random walk, which has an equal probability to advance in any direction in the lattice, will return to a previous position in the lattice an infinite number of times with probability 1 in 1 and 2 dimensions, but with probability 0 in 3 or higher dimensions. Wiener process, Poisson process. The Poisson process is named after Simon Poisson due to its definition involving the Poisson distribution, but Poisson never studied the process. There are a number of claims for early uses or discoveries of the Poisson process. At the beginning of the 20th century, the Poisson process would arise independently in different situations. In Sweden, 1903, Philip Lundberg published a thesis containing work now considered fundamental and pioneering, where he proposed to model insurance claims with a homogeneous Poisson process. Another discovery occurred in Denmark in 1909 when A.K. Erlang derived the Poisson distribution when developing a mathematical model for the number of incoming phone calls in a finite time interval. Erlang was not at the time aware of Poisson's earlier work and assumed that the number of phone calls arriving in each interval of time were independent to each other. He then found the limiting case, which is effectively recasting the Poisson distribution as a limit of the binomial distribution. In 1910, Ernest Rutherford and Hans Geiger published experimental results on counting alpha particles. Motivated by their work, Harry Bateman studied the counting problem and derived Poisson probabilities as a solution to a family of differential equations, resulting in the independent discovery of the Poisson process. After this time, there were many studies and applications of the Poisson process, but its early history is complicated, which has been explained by the various applications of the process in numerous fields by biologists, ecologists, engineers, and various physical scientists. Markov processes. Markov processes and Markov chains are named after Andrei Markov, who studied Markov chains in the early 20th century. Markov was interested in studying an extension of independent random sequences. In his first paper on Markov chains, published in 1906, Markov showed that under certain conditions, the average outcomes of the Markov chain would converge to a fixed vector of values, so proving a weak law of large numbers without the independence assumption, which had been commonly regarded as a requirement for such mathematical laws to hold. Markov later used Markov chains to study the distribution of vowels in Eugene Onegin, written by Alexander Pushkin, and proved a central limit theorem for such chains. In 1912, Poincare studied Markov chains on finite groups with an aim to study card shuffling. Other early uses of Markov chains include a diffusion model, introduced by Paul and Tatiana A. Renfist in 1907, and a branching process, introduced by Francis Galton and Henry William Watson in 1873, preceding the work of Markov. After the work of Galton and Watson, it was later revealed that their branching process had been independently discovered and studied around 3 decades earlier by Irene Jules Bioname. Starting in 1928, Maurice Fréchet became interested in Markov chains, eventually resulting in him publishing in 1938 a detailed study on Markov chains. Andrei Kolmogorov developed in a 1931 paper a large part of the early theory of continuous time Markov processes. Kolmogorov was partly inspired by Louis Bachelier's 1900 work on fluctuations in the stock market, as well as Norbert Wiener's work on Einstein's model of Brownian movement. He introduced and studied a particular set of Markov processes known as diffusion processes, where he derived a set of differential equations describing the processes. Independent of Kolmogorov's work, Sidney Chapman derived in a 1928 paper an equation, now called the Chapman-Kolmogorov equation, in a less mathematically rigorous way than Kolmogorov, while studying Brownian movement. The differential equations are now called the Kolmogorov equations or the Kolmogorov. Other mathematicians who contributed significantly to the foundations of Markov processes include William Feller. Lévy processes. Lévy processes, such as the Wiener process and the Poisson process on the real line, are named after Paul Lévy, who started studying them in the 1930s, but they have connections to infinitely divisible distributions going back to the 1920s. In a 1932 paper, Kolmogorov derived a characteristic function for random variables associated with Lévy processes. This result was later derived under more general conditions by Lévy in 1934, and then Khinchin independently gave an alternative form for this characteristic function in 1937. In addition to Lévy, Khinchin, and Kolmogorov, early fundamental contributions to the theory of Lévy processes were made by Bruno de Finti and Kiyoshi Ito. Mathematical construction. In mathematics, constructions of mathematical objects are needed, which is also the case for stochastic processes, to prove that they exist mathematically. There are two main approaches for constructing a stochastic process. One approach involves considering a measurable space of functions, defining a suitable measurable mapping from a probability space to this measurable space of functions, and then deriving the corresponding finite-dimensional distributions. Another approach involves defining a collection of random variables to have specific finite-dimensional distributions, and then using Kolmogorov's existence theorem to prove a corresponding stochastic process exists. This theorem, which is an existence theorem for measures on infinite product spaces, says that if any finite-dimensional distributions satisfy two conditions, known as consistency conditions, then there exists a stochastic process with those finite-dimensional distributions. Construction issues. Resolving construction issues. One approach for avoiding mathematical construction issues of stochastic processes, proposed by Joseph Dubé, is to assume that the stochastic process is separable. Separability ensures that infinite-dimensional distributions determine the properties of sample functions by requiring that sample functions are essentially determined by their values on a dense countable set of points in the int. Furthermore, if a stochastic process is separable, then functionals of an uncountable number of points of the index set are measurable and their probabilities can be studied. Another approach is possible, originally developed by Anatoly Skorokhod and Andrei Kolmogorov, for a continuous time stochastic process with any metric space as its state space. For the construction of such a stochastic process, it is assumed that the sample functions of the stochastic process belong to some suitable function space, which is usually the Skorokhod space consisting of all right continuous functions with left limits. This approach is now more used than the separability assumption, but such a stochastic process based on this approach will be automatically separable. Although less used, the separability assumption is considered more general because every stochastic process has a separable version. It is also used when it is not possible to construct a stochastic process in a Skorokhod space. For example, separability is assumed when constructing and studying random fields, where the collection of random variables is now indexed by sets other than the real line, such as n \n dimensional Euclidean space.